Hello and welcome to the third episode of my genetic genealogy blog. And today's topic is going to be an advanced one. It's advanced because we're going to manipulate directly raw data. So let's define phasing. When most people speak of phasing, they refer to determining which of the two alleles inherited at a given SNP come from each parent. So let's say you have a G and a T at a certain SNP or row in your raw data file. And at that same SNP, your father has a G and a G, having been passed a G allele from both of his parents in that situation. So what it looks like, I have it here in this chart, a G and a T for the child, and a G and a G for the father. In this case, you know the G must have come from the father, as that's all he had to offer, right? And therefore that your T came from your mother's side. And this is really basic phasing. It gets a lot more complicated than this, but this is what phasing means. As you see, you can often predict the maternal allele even when the mother sample is not available for examination. So you don't need both parents to phase. Here, just to note though, there's only one maternal allele that's predicted, and that's of course the one that the child inherited. Of course, the mother, like the father, had two maternal alleles. Now that you've seen an example of how phasing works, let's expand our definition of phasing a little bit. The term phasing refers to the fact that an allele is in phase between the two samples identified. Here, the G allele, which is exhibited by both the father and child. Isolating the in-phase stream of DNA, if that's what you want to call it, is called phasing. It doesn't have to be parent-child, but that's the most common application. But there are a lot of other applications to phasing that we're going to talk about in this series. One can phase the DNA between any relatives over the span of a matching segment of DNA, or multiple matching segments. So the only requirement, if you want to phase the data of two individuals, two donors, is that they have at least one matching segment. And of course, you could only phase the kits over the span of that matching segment. But it doesn't have to be, a parent, child, or brother or sister, or anything like that. Also, a lot of people throw around the word visual phasing, and this is something different. I'm talking about actual phasing, about isolating alleles from the raw data file that are shared or in phase between two individuals due to inheritance. The analytical tool that we need to understand in order to perform phasing manually in Excel is referred to as Boolean Algebra. And Boolean simply means dealing with expressions or variables that are either true or false. They're binary in nature. So like an integer is not a Boolean expression because there can be an infinite number of integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Whereas if you only have two choices, 0 or 1, or true or false, then we're talking about a Boolean expression. Boolean algebra is computed using formulas in Excel, similar to other formulas. And I don't know what background each of the viewers is going to have in Excel formulas, so I'll go through some basics on Excel formulas, at least the types of formulas that we're going to use in phasing, and creating a phasing algorithm here. Every Excel formula begins with the equal sign. That is how you tell Excel that you want to enter a formula. So instead of just typing 1 plus 1, which will just display literally 1 plus 1 in the cell, you type in equals 1 plus 1. And then that will actually compute the value of 1 plus 1. And you'll see at the top, if you click on the where I wrote value in here, if you click on it and then look at the top, it'll actually show you equals 1 plus 1, whereas it'll show the number 2 in the text of the spreadsheet itself. So if you want to edit a formula or something, you do it up there in the top. When I do a formula here, just for ease of showing it to you, I've made a separate column for the formula, in text form, and then the value as it's computed by that formula. So first formula we're going to look at, equals 1 plus 1. Simple. It returns a value of 2. This isn't a Boolean algebra or anything like that. This is just how to do a formula in Excel. Equals 3 divided by 4, it gives you 0.75, so it'll spit it back to you in the most appropriate, form, in a decimal form in this case. And the slash is to divide, the asterisk is used for multiplication, but other than that, most of the symbols are the same as in regular math. If you want to indicate the order in which calculations are done, or just to make formulas easier to read, I like to use parentheses. And they kind of make it easier to follow, even sometimes when they're not when they're a little unnecessary. Like here, I think you'd get the same value 9 for 1 plus 2 times 4 with or without the parentheses, but it makes it easier on someone looking at the spreadsheet to see what exactly it is you're calculating and what is the intended order of operations. Now, the last one in this box equals C12 plus C13. I've added up the values in Excel's cell Excel's cell C12 and cell C13, the 2 plus the 0.75. So you don't have to actually use numbers in the formula. You can refer to other cells, and this is vital for our purposes. Okay, so let's get into some actual Boolean algebra. In Boolean algebra, we apply Boolean operators to expressions, resulting in a true or false as the output. We also use conditional operators, and we'll get to that, to express output in terms other than binary values of true or false. In the abstract, this may sound a little complicated, but in application it's really not. It's manageable. Let's turn to our first Boolean operator, which is the equal sign, something we're pretty familiar with. The equal sign has two purposes in Excel. Remember, it also shows Excel that you want to enter a formula, but that's not what I'm talking about here. I'm talking about the actual equivalency or identity. The equal sign is the identity operator in Boolean algebra in Excel. So it basically tells you, it returns a value when you enter two things on the side, on each side of the equal sign, whether or not they're actually equal. So if you put in equals, just first to start, to show that we're entering a function or a formula, and then in parentheses, 1 equals 1. You don't need the parentheses, but again, I like to make it clear, make it readable. The answer is true. 1, in fact, equals 1. If, on the other hand, you put equals 1 equals 0, it's going to return a value of false because 1 does not equal 0. Or if you put 1 equals 2 or 1 equals 3, the Boolean value that's outputted by this Boolean operator is false if they are not equal. Now, we can put a couple other kinds of things in here. We don't have to put numbers. We could put letters, which is very important for us, as you might imagine. And when we use letters, we put them in quotes. So G equals T is going to say no, false. But G equals G is going to return a value of true, because G in fact equals G. And again, we can do this with the cells that contain those values of G and T. Okay, let's apply some formulas to some actual DNA, or to some allele values. Again, going back to that example where the child has G and T, and the father has G and G. Okay, so how can we evaluate equals B26 equals C26? So we have the identity operator, and we want to know if they're identical. Are the contents of B26 and C26 identical? No, this is false, because the contents of B26 is the letter G, and the contents of C26 is the letter T. Now how about equals D26 equals E26? Are they identical? Yes, they both equal G. These are the father's two alleles. And we're not phasing yet, but we're learning how to apply these operators to DNA data. Okay, now we'll learn a new operator, AND. It's just like it sounds. It only returns a value of true if both arguments are in fact true. So this has to be true and that has to be true. Otherwise, it's false. So here we go, and B26 equals G, comma, C26 equals G. For the AND operator, you separate the arguments with a comma, and you put them in parentheses. A little different than the equal operator. And that's false, because while B26 does equal G, C26 does not. It equals T. So one of those is wrong, and that's just as good as if they're both wrong for the AND operator, because they both have to be true, this one and that one, to return a value of true. Try D26 equals G and D26 equals G, comma E26 equals G. That's true, because they both equal G. This one equals G and that one equals G. That's why it's called the AND operator. Now, OR is pretty self-explanatory. It's just like the AND operator, except only one has to be true. So, OR A comma B means either A is true or B is true. Okay? Here, OR B26 equals G, comma C26 equals G, that's true, because the first one is true, that B26 equals G. Doesn't matter that the other one's not true, because it's just one of them has to be true. This one or that one is true. Or D26 equals G, comma E26 equals G. Now here they're both true, but that's fine too, as long as one of them is. Also, there's no limit to the number of things you could separate by commas in here. I mean, there may be a limit, a theoretical limit as far as your computer can process, but you can require 3, 4, 5 arguments to be true for the AND operator. You know, you can say this one and that one and that one and that one all have to be true. Or you could have, 10 choices for the OR. A, B, C, D, E, F. This one, A or B or C or anything. If any one of them is true, it'll return a true value. And remember, in Excel, the AND and OR operators take their arguments in parentheses, separated by commas. And that's it for Boolean Algebra in Excel. There's really not much more to it than that. If you need to review it, you can. But now let's revisit phasing. In the beginning of this tutorial, we looked at one scenario where it was obvious which allele was in phase between the two relatives. That is, we could just eyeball it and we could see the child had GT, the dad had GG. He must have got the G from the dad, because that's all the dad had was G's, okay? It's not always that obvious. For example, what if the father has a G and a T, and the son has a G and a T? In fact, that's flat out ambiguous, and with that information all by itself, you can't phase that line of data, and we're going to insert something called a no-call in that situation, where you can't make a call as to which one is paternal or maternal. There are ways of getting around it, or reducing the number of no-calls in phasing, especially by using siblings and other close relatives and doing, duplicate work, basically, to fill in some of the holes. But keep in mind that we will have to return a no-call in a situation like this, it's called, because we can't make a call as to what the paternal allele is from this information. The value used in Ancestry.com kits for a no-call is 0. And that's what I like to do, just because my first kits were all in Ancestry, although I've branched out since. Other companies may use a dash or a question mark. Also, some of the other companies may put the two alleles in the same cell. And that's a little annoying, but we'll deal with that in another episode, how to adjust for that. But right now we're looking at something that you might see in, say, an Ancestry kit. So here, the predicted in-phase paternal allele and out-of-phase maternal allele should both be reported as 0 when we make our phased output. Our task in writing a simple phasing algorithm is to take in all these different scenarios, all the possibilities, such as the two described above, and there's some more, and convert them into Excel formulas that produce, or into a single Excel formula that produces the desired phased output. Although there are 3 possible outputs to a phasing problem or phasing function, assuming the SNP is part of a matching segment, there will always be an in-phase allele, right? Because by definition, a matching segment has at least one allele that matches the whole way through. Then there'll always be 2 other alleles that aren't in phase. The one allele would be, in our example, the allele that the child inherited from his other parent, and I call that the out-of-phase allele. And then the other allele that we could produce as output if we should so desire, and there are many applications for it, is called the evil twin allele. And that is the allele that the parent did not pass to the child, because the parent only passes one of its two alleles to the child at any given point. And I'm trying to use terms like evil twin and in phase and out of phase instead of maternal and paternal, because like I said, you don't have to use only parent and child. So I'm trying to avoid that type of terminology here. So let's go back to our original example and see how the labels apply. The child's allele 1 and allele 2, G and T. The father, G and G. The in-phase allele is G. The out-of-phase allele is the letter T. And the evil twin allele is a G also, because that was the dad's extra that he didn't pass. He had 2. So now that we know the desired output for our function, let's build it. Okay. We're going to need to know about conditional operator. It's called if. Basically, if this condition is true, then return a value of A, and if it's not true, or else, return a value of B. Okay? So it has 3 arguments. It has the first argument is a Boolean one that could either be true or false. And then it has 2 output arguments, one to be displayed, if you want to say, or returned, if the Boolean expression is calculated to be true, and one if it's calculated to be false. And you set those possible outputs. Okay, so here's a simple one. We have, as in our input column here, day, night, and evening, different times of day. And our formula is going to be if B6 or B7 or B8, I copied it down, so when I copy a formula, it automatically updates the row number, so I don't have to retype it every time. So that's really nice when you copy and paste in Excel. So basically, if the contents of whatever cell is in column B is day, if that's true, then I'm going to say good day. If it's false, it's going to output good night. So for the first example in row 6, day is our input, and it says good day. It returns the true outcome or output or argument. Then we'll try it with night. And since that B7 equals day is false in that instance, because B7 in fact equals night, it will return the false value, good night, rather than good day. So the 3 arguments for the if operator are a Boolean expression, and then the positive or true output, and then the negative or false output. Now, remember, it's a Boolean expression. So if you say evening, it's not going to say good evening. It's going to evaluate whether evening equals day, and it's going to find that that's false. And so it's instead going to say good night. Evening's kind of like night anyway, but it doesn't know that. So if perhaps you said morning, it would say good night with this particular formula. When a function is used as an argument within a function, we refer to it as nested functions or nested formulas. You could think of those Russian or Polish nesting dolls where there's one inside the other, and that's how you'll remember this. So we have nested formulas. Here's an example of a simple nested formula that analyzes whether the name in column B is correctly paired with the gender in column C. Now again, Excel has no idea what a boy's name or a girl's name is. Take a look at this table and see if you can't figure out how it works. There are 3 formulas on each line nested within each other. One if on the outside, and then on the inside, for the Boolean expression, we have an OR operator nested in there. And then for the true value, we have an if operator nested in there. For the false value, it's a girl. So the test, or the condition to be met, is or B23 equals John, or B23 equals Jim. So boys' names. And the correct value is, if the second column was a boy and you actually got it correct, and it's correctly matching information, then correct. Otherwise, incorrect, it's a boy. Otherwise, if it's not a boy's name, it returns, it's a girl. There are two things that I want to expressly point out here. The first is that when you nest one formula inside of another, you don't need to use the equal sign on the one on the inside. That first equal sign only goes at the beginning of the entire formula. Once you type that one, it already knows that you're talking about a formula. And if there was any ambiguity, whether it was some text that looked like a formula or a formula within there, you'd be using quotes if it was text, or if it was, not numerical or formula. Okay, so the second thing is that if you only include the conditional Boolean argument and then one output argument, it'll assume that's the true argument. So for example, if sky equals blue, comma, day, it will return day if sky equals blue, and it will return false if sky equals something other than blue. So it just spits out false if you don't satisfy the condition, but you don't specify what the false value is. Here's a little chart that has a variation of the previous gender predictions, and I took out the second output argument, which is the third argument, and you'll see in the third case there it registers as false as opposed to it's a girl in that situation. Okay, now back to DNA. The best way to learn to write a phasing algorithm is to just learn by doing. Let's start simple. Here both of the child's alleles are the same, so the child received one G from his father and the other from his mother. So child has G and G, father has G and T. So the formula that we can come up for this very basic situation is if B7 equals 6-7, if B7 equals C7, if the child has two alleles that are the same, then for the in-phase allele for the output, simply return the value of B7. You could have said C7 since they're the same, but just return that value. Because they must have got it from the parent, because he got the same thing from both parents. Okay. Here the value would be G, the output. And now let's take a second scenario and add it to that. Add it to the mix. Child allele GG, father's alleles GT. Okay, we just did that. Now the second one here, GT for the child and GT, right? So we talked about that before. It's impossible to call. It's a no call. So we want to have it output in that situation the number 0. So if this was the full expanse of possibilities, permutations here, we're going to make one unified function here, or formula, that will return the value of G for the first scenario and the value of 0 for the other scenario. So if B11 equals C11, then return B11, and if not, return 0. Because in this little universe where there's only two possibilities, it's one or the other. It's either returning the G or returning a 0, because they can't tell. All right, let's go down a little bit further. And when it gets more complex, I like to use what I call a placeholder sometimes, just so I can keep track of my thoughts. So the placeholder I'm going to use here is let's calculate it later. All right, so GG and GT, we've already looked at that. GT and GT, okay, that's the insolvable one, right? Now we've got GT and GG. Well, that's easy. We looked at that, I think, earlier too, and that we know that G must have come from dad and T from mom, right? And then the GT and the TT, that's not much different, except we know that the T must have come from dad and the G from mom, right? So let's come up with a formula that encompasses all of that, but we'll leave the value for those last two to calculate later. So if B20 equals C20, then return B20. Or else it returns a conditional value. It returns if D20 equals E20, let's calculate it later. So it can calculate it later if it's that other scenario where the parent has two the same. Otherwise, put the no call. And last, when you insert an if nested in like that in the last position, in the else position, in the negative output position, what you end up pretty much is a list of next best choices. So if B20 equals C20, bam, the answer is B20. Now, otherwise, if D20 is E20, then the answer is let's calculate it later. Otherwise, just put a 0 because we don't know. That's what all of this table means here. But there's no time like the present. Instead of calculating it later, let's make a substitution. In the case where the two parents have, where the two paternal or father's alleles are the same, and just pick one of those, and that's our answer, right? Because if the father has G and G, then the answer to which is the paternal gene is the G. So let's replace that with the value in column D. And again, I could have picked column E because it's the same as column D in that situation, right? But I had to pick one, so I didn't really think much about it. So here, let's see if it works, because now we have the same formula just cut and pasted down in the 4 scenarios, right? In the top rendition and on row 29, it's if B29 equals C29, then B29. Otherwise, if D29 equals E29, then D29. Otherwise, return a 0. Right? Okay, so GT, the answer is G, right? The kid has 2 G's, he must have got one of the G's from the father. All right, next layer. GT, we talked about that. Impossible to figure out which is which. 0. So far, so good. How about GG? Well, he must have got the G from the father because that's all the father had. And the formula got it correct there. Picked the correct value of G. And now the last one here, GT. All the father had was T's, and so it was correctly assessed by the formula as a value of T. And this is the simplest formula that can be used to phase a parent-child. It's not the best formula, but it's the simplest one. Let's make a formula to calculate the out-of-phase allele, and the evil twin allele too while we're at it, for the same sets of values, now that we have some experience in writing these types of formulas. I'm going to go through this portion a little quickly not because it's any less important than the in-phase allele, but because it's easier. Because we are already armed with some knowledge. In particular, we're armed with the knowledge of what the in-phase allele is. When we're coming up with our formula, we can take advantage of that and just use that as part of our as one of our inputs for our new formulas for the other alleles. Okay, so let's take a look at the out-of-phase allele. Remember, what is the out-of-phase allele? It's, in the case of parent-child, it's the allele the child got from the other parent, from his mom in this case, right? So it's kind of simple how you resolve that. If you already have the in-phase allele, it's just whatever one that the child didn't get, right? It's the other one. So if the in-phase is B, is B14, then the out-of-phase must be C14, and vice versa. So we put that into a formula, and it's if G14 equals 0, then 0, right? Because if it's a no-call as the in-phase, we have no idea what the out-of-phase either. It could be the same. It's equally ambiguous. But other situations, let's calculate it. And we nested the if in there because it's like a let's calculate it sort of substitution. If G14 equals B14, if the in-phase is the first one for the kid, then return C14. Otherwise, if not, return B14. Right? And it works. We get G. We get the other one. It also happens to be the same as the paternal one in this case, but not always so. All right, so let's look at the next one. It returns 0 because that's the situation where they're both ambiguous. And then in the third example there, GT, GG, the in-phase allele is G, and the out-of-phase, the maternal one in this case, is T, because the father had 2 Gs. So if G16 equals 0, then 0. That's not the case here. So otherwise, if G16 equals B16, pick C16, pick the other one. Instead of picking G, because we know that's the in-phase, pick the T. That's it. Easy as that. And it's not any harder for the evil twin one. The only thing is, instead of looking at the child's other, the one that's not in common with the father, we're looking at the father's allele that's not in common with the child, the extra one that the father did never pass to that child. The same thing, except instead of looking at the opposite of, returning the opposite of, E3 instead of D3, and D3 instead of E3. So we're just looking at 2 different columns. We're looking at D and E now instead of B and C. You see that. Let's go through one of them in row 23. If G23 equals 0, then 0, right? If it's a no call for 1, it's also still a no call here, no call all around. Otherwise, if G3 equals D3, if the in phase is the father's first allele, then return the second one, return the other one, return E3. Otherwise, return D3. And at the bottom, I combine them just to have them all in one row, because that's what we're going to want to do in real life when we look at actual raw DNA data in one of our later episodes, or in a lot of our later episodes. Why? Why do we want them all in one row? Simply because you don't have to add or insert any rows or anything like that. We could just put these formulas right in the raw DNA files and have it calculate it right next to the real data there. Okay, so now for a homework assignment. By the way, I know that I said I had a homework assignment from last week's, and that I was going to take all of Uncle Pete's individual chromosomes that we made with the Lazarus kit and combine them into one. And I didn't. I made a liar of myself, and I didn't quite have enough time for that because I was working on another project actually involving Uncle Pete. So instead of doing an addition of Lazarus kits, I actually used these phasing formulas to phase and make a sort of an ancestry style kit in Excel for Uncle Pete, and which is nice. I'm still going to do the Lazarus one, like I said, but it would be nice because we're going to have something to compare it to. We're going to compare the Lazarus method versus this phasing method in a future episode and see what's the benefits of one versus the other. They both have their benefits. They're both different processes. Okay, well, anyway, the homework this week, and in all fairness, I didn't do mine last week, and you don't have to do this homework, but I had mentioned briefly that this is the simplest phasing algorithm for parent-child phasing. Simplest in a couple ways. I mean, it's very short, and it covers the basic scenarios, and it's pretty low as far as intensity on your processor for performing the math on your computer and taking up a bunch of memory. So it's pretty clean. It's short. It's easy, relatively easy anyway. But your homework is to come up with one that's a little more complicated and that takes into account a couple interesting situations. So your homework is going to be to handle a couple more advanced scenarios. The first is when you go into a raw DNA file, like from Ancestry.com or from any other companies, there are but there are no calls in the raw data itself that don't occur from doing math, like we're doing here, but just because the chip was unable to make a call for one technical reason or another. We don't really need to concern ourselves right now with what those reasons are, but we got to deal with them because we don't want our phasing program to produce meaningless results in there and screw up our nice analysis on whatever kits that we're doing. It has to be able to deal with a situation where it reads a no call as input. So I'll tell you one thing to make your life easier is that at least in the Ancestry ones, and I'm pretty sure in all the companies, if the chip returns a no call for the first allele, it also returns for the second. So there's never a situation where you have like a 0G or T0. If there's a 0 and 1, it's always 0, 0. So that makes a little less work for you. Okay, and then let's deal with the second possibility too, and that is if there is, let's say the kid has TT, the father has GG. Well, what happened there? One of two things happened: a mutation or a miscall. Chip made a mistake. It improperly read something. That happens. There's another reason too. There's something called micro deletions and things like that, but we don't need to get too involved. All we need to know is that we need to identify that as an error or as a non-matching SNP. We'll write error just because it's a shorter word, and it's not really an error so much as it is just a mismatch for one reason or another, either a genetic mistake or a mistake of the chip. So, for homework, I want you to add these 4 scenarios into well, I said 4, but I only talked about 2. That's because there are different places where those no-calls can be, right? The no-call can be in the child, or the no-call can be in the parent. And within each of those, the no-call could be in a situation where it's still obvious what you inherited from the father, because the kid only has 2 of the same allele. So even though the father has 2 no-calls, you know what he got from the father, so, right? And then the other situation is where the kid has 2 zeros, and the father, say, has G and T, right? So what are you going to do with that? You can't tell which one the kid got. You don't know what the kid has, and he had multiple choices from that parent. I mean, maybe if the mother was alive to test, but that's not the program we're working on today, the formula we're working on today. Just one parent phasing. So I made a little table down there that identifies what the values should be, for each of those scenarios, and I included, I guess it's a total of 5 scenarios, 4 scenarios of the no call and 1 scenario of the mismatch. So, and by the way, this is not just hypothetical, or it's not just useful for pointing out, an error, because there's only going to be so many errors throughout the kit, right? If it's mother and child, it's not like the child's mutating left and right all over the place, and in reality, there's only going to be maybe 1 miscall on each chromosome or so on most people. But what it's useful for is when we go to our next lessons on cousin phasing and Lazarus phasing and all the other kinds of phasing that you can do with the relatives other than parent and child. Because that little error situation, when you get like bundles of errors, that's going to show you where the segments match or don't match. Where they have errors between frequently, that's going to be a non-matching segment. And where they don't have that word error come out in the output, that's going to be the matching portions of the segment. So you'll be able to tell where the matching segments begin and end without using a GenMatch or without using another tool yourself in Excel. Of course, you'd have to have the raw data. You can't do that with all your GenMatch matches, but you could do it with the raw DNA kits that you have access to. Okay, and I'm going to give you 2 hints for your homework assignment because it's kind of a hard one. The first one is you want to make a table of all possible outcomes, including the no calls, including the new ones, including the old ones that we already went through. And you can stick to G and T because in real life there are other ones like C and A. However, they don't. There's only 2 possible in each row, and we're not referring to them by name here. We're always referring to the contents of the cells being either equal or not equal. So they're going to work equally well with SNPs that might have an A and a T. It's the same concept. We don't need to write new formulas for that. They'll work. Okay, second hint. The and not operators will make your life easier for this assignment. You're going to need to do some nesting. For sake of making this easy to find, should you want to come back to it later, I'm going to put the solution to the homework in this video. So close your eyes if you haven't done it yet. But here is a chart with all of the possible outcomes here. I'm going to scroll through it slowly. Well, there's not much to scroll through here. So there are 24 possible outcomes. Two of them will have that error that we talked about where, TT and GG and GG and TT, right? Because that means that the parent was incompatible with the child. It was never in phase with the child for one reason or another. Now let's take a look at the formulas. For the in-phase formula, I won't say it out loud, but you can read it, copy it down. If you want a copy of this spreadsheet, I'd be happy to email it to you. Just let me know. Contact me and I will be happy to send you a copy. There's the formula for the out of phase. Note how I handled the error first. And in the first one, I had a series of conditions which defined the error. And the second one, to make my life easier, I just looked at whether the first one had an error, because an error for one is an error for all these columns, right? There's the evil twin solution. All right, until next time.